Yeah, hi everybody. I'm Allan Smith. I'm the low carbon manager at Galliford Try. So I'm going to talk about how we as a company have been looking at our Scope 3 emissions and how we've been collaborating and using data to analyse that and understand our footprint a little bit better. So Scope 3, the challenges. This is a graph. It's called the Dunning-Kruger effect, and it's like a cognitive optimism bias graph that explains that when you're starting in a project and you maybe don't have much experience, you overinflate your confidence about how you're going to tackle that. And I think that kind of fits in quite nicely with Scope 3, because a few years ago when we started looking at how we set our Scope 3 targets, we thought, let's calculate everything. They are what they are, upstream, downstream, let's just go for it. But then very quickly, you realise that that's a hell of a lot of information that you need to deal with. Your own bot emissions, your client's emissions, and just everything else in between. So it was really thinking, there's no way we're really going to be able to fully do that justice and understand that. So where we are as a company at the moment is understanding where the big wins are as a Scope 3 emission, and then really trying to understand them a little bit better and just work with those ones. So we are in between the two last points there. So we're in the collaborate and deliver phase at the moment, now that we've settled on what the big wins are, and I'm going to obviously touch on them as we go through. So our Scope 3 are very much linked with our clients' embodied carbon targets. Not all projects have embodied carbon targets, but where they do, most of our Scope 3 emissions sit within those. So when we work with clients, they've got industry-led targets, whether that's the new UK net zero standard or whatever their individual targets are. And then our Scope 3 reporting sits within that as well. So as a company, round about 97% of our emissions sit within our Scope 3. Scope 1 and Scope 2 are obviously very, very small. And we've decided as a company, for our Scope 3, we're just going to focus almost purely on steel and concrete. Steel and concrete make roughly about just under half of our actual carbon emissions themselves in terms of our bought products. So it makes sense to just really focus and understand that and deliver those properly as well. Obviously, you get a much sliding scale as you go down the material hierarchy, so that's where we are focusing at the moment. So steel and concrete, but I'm just going to focus on steel just by way of example here as well. So this is a diagram just showing the UK glide path for the decarbonisation of steel. So on the left-hand side there, you can see 1.74. So that's roughly, if you specify UK steel, you'll get a blend of blast furnace steel and electric arc furnace steel. So the carbon factor is about 1.74 at the moment, and it's gradually making its way down through to 2050. So we have an interim target for our Scope 3 at 2030. And we've set our interim target as 0.93, which is the 2035 industry target. So that kind of tells us that we can't just rely on continually specifying just standard specification steel. We need to actively look at interventions about what we do with our projects. So I'm just going to go through. So we did a study on. We primarily do we do lots of educational buildings. So we did a study on about a dozen of our educational buildings across the UK. Not all of these had embodied carbon targets. We just wanted to understand what business as usual was for us, and what made up those buildings from an embodied carbon perspective. So this was the result here. Figures are quite small, but each one of those there, and just to put it into a few pieces of context. So up in Scotland, we have a net zero public sector building standard, which sets the target at 600 kilograms of CO2 per metre squared. The UK net zero carbon building standard 2025 target is 530 kilograms of CO2 per metre squared. So you can see there that not many of our buildings were actually meeting either of those targets. There was only a handful which were just down about that level, and almost none of them were actually meeting the current UK net zero carbon standard. So that allowed us to understand, well, we can't just carry on doing as we're doing, so how do we use one-click software to break that down and analyse where the big wins are from there. And also, for further context, the UK net zero carbon standard, it has a year-on-year depreciation as well. So that's the target for 2030, so 395. So there's quite a big jump that we need to go down, certainly from a client perspective, and then also from our own Scope 3 perspective as well. So I've removed the foundations because I'm not speaking specifically about concrete at the moment, but the red is essentially the superstructure of the frame there. So you can see more or less the superstructure makes up about 40 to 50% of the overall carbon element of the superstructure of the building. So that just kind of reinforces to us where, you know, focusing on steel is the main thing. And out with that red marker as well is in the envelope we've got SFS, steel SFS, we've got metal in the partitions as well. So steelwork actually makes more of a percentage of those ones when you add all those elements on, but that is just primary steel there. So taking the steel element then and looking at this, so again it's quite small, so apologies, but the red bar, the grey bar is the weight of the frame, so we're able to look at the weights of our frame. And then the red bar is the overall carbon factor of the frame as well. So breaking that down, so we were able to understand that the average weight of our frame was 71 kilograms per metre squared. So we've got some that sit higher than that, some that sit lower than that, but fundamentally they're all school buildings. And that now starts to give us a little bit of data and power to say to the design team, well, if your frame is sitting above 71 or 75 kilograms, then there's something maybe inherently inefficient in that frame. So what can we do? Is it transfer structures, cantilevers? Can we reduce that down because we can demonstrate that we can meet more efficient frames there? So that is the biggest element there in terms of reducing carbon. But then also the frame intensity is sitting at an average of 120. But I think here you see the biggest difference between the bars, and that's because in the schools where we've got the lowest carbon intensity on our frames, that's where we've been proactively specifying electric arc furnace steel for the projects. So they've really focused on frame efficiency and the specification of steel. Whereas the higher ones, they've been higher weights of frames and just UK standard specification steel. So you're multiplying everything by 1.74 effectively as well. So that allows us to sort of really drill down and I guess appreciate that there's huge differences that you can do in terms of design and in specification as well. Not expecting anybody to see these figures, but this is just an example of a report that we got for one of our schools that is just under construction at the moment. Hopefully that's going to play. Okay, but essentially what this report now has is that's basically every line there is a member of steel on the project, and it tells you what factory it comes from, what the carbon intensity A1 to A3 is of that steel, what the transport emissions are from the factory to our supplier. So we can really get into the nuts and bolts of the individual members and the optimization of the frames that we do there as well. So these are great tools that we can then take the data that we've got in one-click, for example, and then substitute it in with the actual as-built data for our frames. And just by example, so this is the same project here, Paisley Grammar up in just outside Glasgow in Scotland. So this was a report that we got, and it's shown that we got supplied 950 tonnes of steel, and the A1 to A3 embodied carbon figure is just under 1,000 tonnes, which gives us an overall embodied carbon factor of 1.117. So this is a project where we've really been pushing the design, we've been pushing the specification of the steel. But when I go back to the previous graph on the steel, our target is to get to 0.93, whereas on a project we're sitting at about 1.117. So it just shows that we've got quite a lot of work to do to really get to that 2030 target And yeah, I think your steel might be quite useful for that as well. So yeah, I think the industry is going to obviously decarbonise with us, but for us, we understand that the designers have a lot to do with that as well, to really push the reduction down. And then just really finishing on this slide, so the PAS 2080 hierarchy is avoid, switch and improve. So what are we doing around each of those elements? So avoid, so as I've talked about, we've now got that data that from our buildings to where we can proactively try and influence the design decisions that the designers are making. How can we work with the designers, the structural engineers, to just physically reduce the amount of concrete and steel that we're using in our buildings in the first instance before we even look at specification? And then when we do look at specification, how do we collaborate with our subcontractors to understand what are the best products that we can get? When we first started looking at this, we thought electric arc furnace steel specification was going to be more expensive, more GGBS content in the concrete was going to be more expensive, but when you sort of speak to the suppliers and understand where they're getting their supply from, you can really tailor your design to what you can get rather than trying to influence it too much. I think it's a two-way process that you've got to work with what the industry can give you as well. And also improve, embrace innovation and share lessons learned, which is hopefully what we're doing here today as well. Yeah, that was everything from me. So thank you very much.